So because we now learned about the bisection method, we can create an algorithm to repeatedly perform the calculations in iterations with the error check so that we can have the final result. Here you can see a pseudocode for simple bisection algorithm, a function actually. So we will start with an initial XL and XU lower and upper bounds, a threshold for the error, maximum iterations. XR is the midpoint value or the predicted value of the root, iteration number, and the approximated error. So here what we do is actually we call this function at each iteration. That's why we have this XR and iter values as inputs here. Basically what we do is, so we determined an XR based on XL and XU simply by dividing by 2 of the summation of these, and we set it to XR old. Then now we obtain a new XR by dividing these, and we increase the iteration. Then if XR is not 0, this XR is not 0, we calculate the approximated error basically using this, or we can also use XL and XU values as well for in here. And we need to test if the lower bound times XR is lower than 0 or greater than 0. If lower than 0, then upper bound is changing. If greater than 0, then lower bound is changing to the midpoint, the new midpoint calculated here. Otherwise, so if it is equal, then error is 0 and we stop here actually. And if the approximated error is less than this ES value predefined, or the iteration is greater than Imax value, the maximum iteration, then we finish. And finally, we obtain the bisection value as the XR value. So this is a simple algorithm. The features of this algorithm is it employs user-defined functions to make root location and function evaluation more efficient. An upper limit is placed on the number of iterations, the Imax. And this means there is no actual function calculation here. It's basically just XL and XU and division by 2 and checking. Of course, we will have a function calculation here. 2 function evaluations per iteration. So this is actually not efficient because we need to calculate 2 functions. I mean, we need to use the function for 2 times to calculate fxl and fxr at each iteration. And this is good because we have an error check over here. Also, to avoid the division by 0, we have this check here. XR is not equal 0. Because if the bracketing is centered on 0, this can be a problem. And EA becomes infinite. If this occurs, the program skips over the error evaluation for that iteration. So it's just if this exists, it just skips this iteration and moves to the next one. So as I said earlier, this algorithm is simple, but this is not user-friendly because it is strictly come up with a solution for this function only. Whatever function we use, it needs to use that, and also it requires 2 function evaluation. We have better algorithms, and we will talk about those later on. But for bisection, this is a simple general algorithm that you can use in MATLAB as well. In the previous slide, we mentioned about the function evaluations in bisection method, and we said that at each iteration there are 2 function evaluations. And if we are performing a single root evaluation for a function test, that is easy to evaluate, but there are many instances in engineering when this is not the case. For example, suppose that you develop a computer program that must locate a root numerous times. You could call the algorithm thousands and even millions of times during a single run. So that means we need to calculate the function at each time, which increases the computational cost dramatically. Another example, a function is not always simple formula like the one-line equation solved before. So that can be a very complicated equation that you can't even solve easily. That's why solving the function to calculate the root evaluation will not be easy. It might consist of many lines of code that could take a significant amount of execution time to evaluate. And the function might even represent an independent computer program like an finite element analysis or computation fluid dynamics software, and you don't know what's going on behind it, and you don't really want to use a single root evaluation for that function, which is the entire software, and it increases the computation cost, let's say. For these reasons, we need to minimize the function evaluation. So basically, we need to reduce those two function evaluations in the bisection algorithm. An improved pseudocode for bisection method is given in the next slide with minimized function evaluation. So let's go to the next slide to provide a new improved pseudocode for the bisection method. In this slide, we will provide an improved pseudocode or algorithm for the bisection method. On the left hand side you see the simple one, and on the right hand side you see the new algorithm. And here we said that there are two function evaluations, one for the lower bound and one for the midpoint. Over here, on the other hand, what we do is we simply save the lower bound function value from the previous iteration. Then we will have only one function evaluation, and only the new function XR, the midpoint, the new value will be used to calculate the function value, and we will test using the previously saved FL value times FR. So the previous function value is saved already here. Instead of here actually it didn't save the XL value, but here it saves, then takes it as the value over here. Then, so because this is before the do loop, it will be only one function evaluation. So instead of two n function evaluations here, two function times n iterations, here we only have n function iteration here, and the only XL function value is the first XL value, so it's +1. Before the for loop or do loop, we will only have one function evaluation. So we reduce the function evaluations from 2n to n+1, and this is again a very efficient bisection algorithm, and we recommend you to use this to minimize the function calculations.